in terms of the next assignment that you guys are going to work on, there's some actual lecture slide content on it. It's called a Huffman tree. And this is going to, oops, sorry, I jumped to the wrong place. There. I'm just going to spend the last 5 minutes of class. I'm going to give you a quick intro to what your next assignment is going to be about. And you can see a little more about this if you go to the Yeah hours for the assignment, which are, what, Friday? Yeah hours Friday, I think. I don't know. I'll make sure that I have that by Friday's lecture. I think they're on Friday. The assignment we're going to write is you're going to write sort of a mediocre version of zip, of WinZip, a file compressor. And you're going to use a binary tree to do it. You guys know about compression, right? It's where you take big files and you shrink them. And the way that you shrink them is by coming up with some kind of algorithm to run over the contents of the file to represent those contents in a more compact way than their normal representation. There's lots of examples of compression, in mainstream use right now, programs that compress and decompress different kinds of files. What we're going to learn about is compressing text. When you have text data, I think you guys know that text is stored as characters, and characters have these ASCII encodings that map them to integers. So really, text is stored as numbers in the computer. Every ASCII character is an integer from 0 to 255, which means it is an 8-bit integer. So every character takes exactly 8 bits in the computer's hard drive, right? Well, you can make up a different way of encoding the characters called the Huffman encoding, which gives them different lengths depending on what character that it is. I mean, one of the problems with this encoding is that every character takes the same length. What if you could come up with a way that the more frequently used characters were shorter a number of bits and bytes that it took to store them? Then your file would theoretically be smaller if you could do that. And this algorithm we're going to learn about is called Huffman encoding, and it lets you accomplish exactly that. So the Huffman algorithm is you come up with a way of creating a binary tree, sort of in two senses of the word, where you think of the left subtrees as representing zeros and the right subtrees as representing ones. And the way you come up with encodings for characters is by walking down that tree. If you look at the picture on the slide right here, this is a hypothetical encoding where a 0 followed by a 0 represents a space, and a 0, 1, 0 represents a C, and a 1, 0 represents a B, and so on. And these are like hypothetically shorter encodings for some of these characters. How do you do this? Well, I'm going to give you the fast version. It's all written on your spec, basically, for the assignment. But basically what you do is you read in the file of interest. You may use a map to count up how many times every character occurs, every unique character. We've done examples like that before. That's not the hard part. The reason you're doing that is because you want to know which characters are most common, so you can give them the shorter encodings eventually. You count up the occurrences of characters. You turn those character encodings counts into this tree over here, and then you walk the tree to find what character is encoded as what binary, and then you use this mapping to encode the contents of the file. Let's look at a couple of those steps in more detail. Count the characters, pretty easy to understand. If the entire contents of the file are ab, then you look at all the bytes of that and you count it up in a map. There's 2 spaces, there's 3 A's, there's 3 B's. You don't need a binary tree yet for this part. That's not so bad. The only weird thing you do here is you insert one magical character at the end called an end-of-file character. You do that because you need to know when the file's data is done in the compressed stream. We'll talk about that in a second. The second step is you use a priority queue. You guys have just been implementing priority queues. You store all of your characters in a priority queue as a count followed by the character. 1 C, 1 EOF, 2 spaces, 3 B's, 3 A's. And so the priority queue is sorted by frequency, by how often the character occurs. The more frequent it is, the later it comes out when you dequeue from the priority queue. Now you run an algorithm where you repeatedly pull nodes out of this thing. You pull the first 2 out, which are the 2 that have the fewest occurrences. And you put them back in as a binary tree. You put them back in as a parent with both of those 2 as its children. And now the total number of this is the sum of the 2. You pull out the 2 and put them into a binary tree. Now it's 4, 2, 2, 1, 1. And this thing moves to the right edge of the queue because it has more counts than the other things in it. You pull out the 2 3s and they make a 6. Now you pull out the 4 and the 6 and they make a 10. And by building this tree in this way, you are basically storing the encodings for the characters. Because once you've finally built this thing, you can walk left, left, 0, 0 to get a space. And you can walk left, right, left, 0, 1, 0 to get a C. And this is the kind of the backbone of this Huffman compression algorithm.